Okay, so the last couple things that I wanted to talk about, I wanted to do one good example of using this theorem about that ties in continued fractions with solutions to Pell's equation like this. So these P's and Q's with weird indices, these come from that process from last time that I used to quickly compute continued fractions. So let me see if I still have. Yep, I got it. So these weird indices for P's and Q's come from this proposition that defines how I can quickly compute some finite continued fraction like this. Okay, so that's what these P sub mn minus 1 and Q sub mn minus 1 refer to here. And so what this is saying is that if you have the continued fraction for square root of d in front of you, so it looks something like this. It's a naught and then some periodic part, where this last thing in the periodic part is twice the thing you started with. It's twice this a naught. So doing it this way, then so an easier way to remember than try to keep track of these indices is if you're actually doing this process, then if we are looking at the table that computes these things, if I've gotten to the point where my a sub n is double a naught, so let's say it's here at a sub 4. So let's say that a sub 4 is 2 times a naught here. This p sub mn minus 1 and q sub mn minus 1, it's just the p and q from the previous column. Okay, so it's just the previous column here. Okay, that's what you're reading off. So you stop here. Okay, or I should say it's you're computing it up to that point, right? So yes, it's the p and q from the previous column, and that is the thing that gets stuck into your Pell's equation. And of course, there is the possibility that when you use this x and y coming from this process, you get a minus 1 when you look at x squared minus dy squared. But it turns out that in that case, you still end up getting a solution to Pell's equation. And the way that this works is as follows. So like last time, I start with my a naught. So this a naught is just going to be the least integer, or sorry, the greatest integer less than square root of d, right? So this is just I'm just applying the floor function here to square root of d. So second step, so I compute the continued fraction, whatever it is. It's going to be periodic. It's guaranteed to be. And this, so I stop when I get to this a sub n that's twice a naught. Okay. And then I let my x sub 1, y sub 1 be this p sub n minus 1 and q sub n minus 1, like I said. So this is my previous column in that table computing this continued fraction. And so I'm done if it turns out those actually solve Pell's equation. But the other possibility is that they don't. I get a minus 1 here. So what I do to get my x and y is I take my x sub 1 and y sub 1 here, and I write them in this conjugate form, x sub 1 plus y sub 1 times square root of d, and I square that, and I rearrange it into this conjugate form, and then whatever that x and y is, I just read that off from that form, and that will be guaranteed to solve Pell's equation. Okay, so that seems a little confusing written out like that, so let's actually do an example of this. So this will be the only example that I do because I think it gives a good indication for what's going on here. And so on the final exam I posted, I put a Pell's equation problem on there, and I said you could either do this with the Shocker-Weyl method, or you can use continued fractions. So I don't care which, but just use one of those to do it. So let's let d be 13. Okay, so if d is 13, then I'm looking at x squared minus 13y squared is equal to 1. I want to solve this thing. So following this process, what do? I look at square root of 13, right? And square root of 13 is like 3.60555 and some more stuff, right? You can use your favorite calculator to do that. So if you compute the continued fraction for this thing, so as a continued fraction, this is 3, 1, 1, 1, 1, and then 6, and then some stuff. But you don't care because you stop at the point before the 6, right? So 6 is 2 times 3, and so I stop here. Okay, so I compute, so since 6 is equal to 2 times 3, I stop and compute the continued fraction 3, 1, 1, 1, 1. Okay. Now, you could compute that the brute force way of actually writing it as a continued fraction, or you could use that process with the table that I went over yesterday. So, however you do this, you find that this is 18/5. Okay, so what I do here is now I try my luck with x equals 18 and y equals 5. So note 18 squared minus 13 times 5 squared. We hope this is 1, but in fact it is minus 1. So if that had been 1, we'd be done. We would have found a solution to Pell's equation, but it's not. It's minus 1. So what do I do instead? So then I must use step 5 in my process, which had me doing what? So step 5 had me computing 18 plus 5 times square root of 13 squared. So if I compute that, I get 18 squared plus 2 times 18 times 5 times square root of 13 plus 5 squared times 13, and that is 649. So 5 squared times 13 plus 18 squared, 649, minus, so this is 649, sorry, not minus, plus 180, so this is 18 times 2 times 5, so 18 times 10, so 180 times square root of 13. That's what I get. So now I've written it in that conjugate form, so I take this as my x and this is my y, and I check that this actually works. So 649 squared minus 13 times 180 squared is indeed equal to 1. Okay. And so we have actually found a solution in this way. All right, this is a very slick way of doing this Pell's equation type problem. This is a nice, using continued fractions in this way is a pretty convenient way of getting this done. Okay, so I think that's all I wanted to say for Pell's equation. So then one more thing I wanted to talk about in chapter 15 before doing kind of a brief survey of some of the remaining stuff in the text is the following. So I had skipped this earlier, so I'm going back to it. This was actually immediately following Minkowski's theorem, but I skipped it and went to Lagrange's theorem on the every positive integer being a sum of 4 squares. Right. So related to that question, which positive integers are sums of 2 squares? So which integers can be written as a sum of 2 squares? Alright, so I'm looking for positive integers n that can be written as a sum of 2 squares. So I want it to be writable as x squared plus y squared, where x and y are integers. Okay. So first we answer this for primes. Okay, so there's the theorem, and this is actually due to Fermat. So let P be a prime with P congruent to 1 mod 4. Okay. Then there exist integers x and y such that x squared plus y squared is equal to P. And so primes congruent to 1 mod 4 can be written as a sum of two squares. Okay. So to see how this goes, we need a lemma. And so this lemma that we need is something that is true for primes congruent to 1 mod 4, but is not true for primes congruent to 3 mod 4. Okay, so you can think about why this is. So what's my lemma? So let P be a prime with P congruent to 1 mod 4. Then there exists U such that U squared is congruent to minus 1 mod P. How do I prove this? Well, I mean, this is the supplementary law for minus 1 in quadratic reciprocity. Okay. All this is saying is that minus 1 is a square mod P when P is congruent to 1 mod 4, and it is. Okay. Okay, and so we have this lemma. Now, it turns out that when we proved this fact about a positive integer being a sum of 4 squares, we also needed a lemma that was like the analog of this lemma. It was slightly more complicated, but if you remember, we needed the existence of a u and a v such that u squared plus v squared plus 1 was congruent to 0 mod p. Okay, that's what we needed under our assumptions. Okay, so this is kind of the lemma in the same spirit as that. And we used that u and v to define some ellipsoid region, right, that I could use Minkowski's theorem to give me some guaranteed integer point, and that was ultimately how I did the proof. So the idea here is the same. I'm going to use the u that I get from this lemma to construct some region, make sure that it satisfies the hypothesis of Minkowski's theorem as far as the bound on its volume goes. Then I can apply Minkowski's theorem, and that's pretty much going to do it. Okay, so how does this work? So this proof, continuing on here, let u be as in the lemma. Okay. So let B be the set of points in R2, the plane. Such that P x1 plus U x sub 2 squared plus x sub 2 squared is strictly less than 2p. The fact that we use the strict inequality here is important. I'll talk about that in a second. Okay. So now I have a region B defined as this interior of an ellipse. Okay, this area, so volume of B, it turns out is using this fact about how a transformation affects the volume of a region in terms of the determinant of the transformation, if we're talking about a matrix transformation. So using that fact at the end of the first section of chapter 15, the volume of this thing, it turns out, is pi times this radius 2p over p, which is 2 pi. But hey, what do you know? 2 pi is greater than 2 squared. Right? So Minkowski's theorem says that there exists a point x, y not identically 0 with x and y integers, right? Okay, with integer coordinates in B. Okay. But if this point is in B, then it satisfies this inequality, right? So since xy is in B, then it satisfies it satisfies the inequality, so px plus uy squared plus y squared is strictly greater than 0. Why is that? Well, if this thing was equal to 0, then these two things have to be 0, so y is 0. But if y is 0, then x is going to have to be 0. So they would both have to be 0, but we said that wasn't allowed by Minkowski's theorem. We're guaranteed that this is non-trivial. So both x and y can't be 0 here. So this is definitely strictly greater than 0, so it's positive. And because it's in B, by definition, it satisfies that inequality that defines B. So it's strictly less than 2p. Okay, so I have something here that is strictly between 0 and 2p. Okay, but if I actually consider what this thing is mod p, I look at px plus uy squared plus y squared. Mod p, what does this thing look like? Well, mod p, this is 0, right? P is 0 mod p. So this becomes uy squared plus y squared. But this, I can factor a y squared out, and so I have y squared times u squared plus 1. But remember, we chose u specifically so that this quantity, u squared plus 1, would be 0, right? Or u squared would be congruent to minus 1 mod p. So this is 0 mod p, i.e. p divides it. But it's strictly between 0 and 2p. So p divides this thing, this integer that is strictly between 0 and 2p. What does this thing have to be? Right, so the only multiple between 0 and 2p of p is p. Thus, p is equal to px plus uy squared plus y squared, i.e. is a sum of squares. And that was exactly what I was trying to show. Right. Okay. All right. So before I move on and make the general statement, note, just for example, if I say let p be 13, then since 5 squared is congruent to minus 1 mod 13, okay, take u equal 5. So the elliptical region we get is the one that's defined by 13x sub 1 plus 5 x sub 2 all squared plus x sub 2 squared is strictly less than 26. That's 2p, so 2 times 13, 26. But what does that region look like? It looks like that. Okay. And so in this picture, this is a very carefully drawn picture. Okay, so it's an ellipse. Now, this ellipse looks like it includes the boundary, but remember, this is actually an open ellipse. It's the interior of the ellipse. So the integer points have been denoted with these dots. So then this is just a question of how many dots lie fully inside the interior of that ellipse. Well, 1, 2, 3, 4. Right, so 4 points. You might notice that there's some points on the boundary, but those aren't going to be included actually because this is a strict inequality. And it's a good thing that those aren't included because these integer points don't actually solve the equations that they should solve if they were supposed to be included. But what do these points correspond to? So I get a few. So the points I get are points, I should say integer points inside the ellipse are minus 1, 2, minus 1, 3, 1, minus 2, and 1, 3. Or sorry, 1 minus 3. All right, so these, there we go. So those 4 points. So you can just check, right? Like minus 3 squared plus 2 squared is 13. Where did I get this from? Right? Well, at 13 x sub 1 plus 5x sub 2 was supposed to be minus 3, and x sub 2 is supposed to be 2. Right? So that's what I get from this point. Okay, minus 1, 2. Okay. So each of these points is going to correspond to a solution to this. It's going to give you a different way of writing this as a sum of squares. Okay. Now one more quick formula, and then we're able to state the, basically state, not just state, but pretty much prove, or at least see how the proof is going to go, this more general fact. So note, if m is some integer that is a sum of 2 squares, and n is some other integer that's the sum of 2 squares, then m times n is actually ac minus bd squared plus ad plus bc squared, i.e. a product of a sum of squares is itself a sum of squares. I've been pretty loose with the terminology I'm saying here. I'm saying a sum of squares. You might mistakenly believe I mean a sum of any number of squares. So in this case in particular, I'm talking about a sum of 2 squares. Of course, we had a similar fact, right? A similar formula was the thing that finished off our proof of this fact proven by Lagrange that every positive integer is a sum of 4 squares. We had a very similar formula that was more complicated because it was the statement that if you had two positive integers that were the sum of 4 squares and you multiply them together, that itself was also a sum of 4 squares. And so that was a little bit more complicated with the expression, but this is same thing in spirit. Okay, and like that result, as I mentioned, came from the quaternions, a calculation done with the quaternions. This one comes from a calculation done with complex numbers. Okay, and so if you know anything about the quaternions and their relationship to the complex numbers and how one might seek to kind of do a similar thing with complex numbers to get the quaternions in the first place, then it wouldn't surprise you that there'd be this connection between those. Okay, and so this basically says what I want to say in the next theorem. This basically finishes it. Everything else is just some bookkeeping that I'm not going to do. So what have we shown? We've shown that a prime that is congruent to 1 mod 4 is a sum of 2 squares. Okay, so prime congruent to 1 mod 4 is a sum of 2 squares. And if you have two sums of 2 squares, you multiply them together, that is also a sum of 2 squares. Okay, so rephrasing this in a way to characterize completely what it is that's going on here. So let n be a positive integer. And then n is equal to x squared plus y squared for integers x and y if and only if n is a square times a product of primes that are not congruent to 3 mod 4. Okay. i.e. n is a sum of 2 squares if and only if in the prime factorization of n, every prime that's congruent to 3 mod 4 has an even exponent. Why? So let's think for a second. So if we worry that this is not going to work for primes p congruent to 3 mod 4, then why is it okay if those primes show up in the prime factorization? Well, if they have an even exponent, all those primes congruent to 3 mod 4, if they have an even exponent, can all be grouped together. Since they all have an even exponent, they are, a square taken all together. The product of all those primes raised to their even powers, that's a square because their exponents are even. What remains is all the primes congruent to 1 mod 4. By that theorem of Fermat, every single one of those primes congruent to 1 mod 4 is writable as a sum of 2 squares. And by that previous formula at the top of this page, if I'm multiplying a bunch of sums of 2 squares together, pairwise they're sums of 2 squares, and so their final result is itself a sum of 2 squares. So I have a sum of 2 squares times a thing squared, which I can distribute, so I have again a sum of 2 squares. Okay, so that's the proof. I just said that out loud. So the proof we basically just did by the previous formula and just reasoning it out. To be not hand wavy at all, I would have to say a little bit more, and I have to be careful about doing both directions. But that's how it goes. If you want to see that, this proof is on page maybe it's page 366. But what I said is essentially is all you need to know there. Okay, so some examples then. So this implies there's some numbers that can be written as sums of two squares and some that can't. So 65 is 5 times 13. Both 5 and 13 are congruent to 1 mod 4. And 130 is 2 times 5 times 13. Okay. And 405 is 3 to the 4th times 5. Oh yeah, that's it. These are sums of squares. Okay, and you can try to find those quick. If you want to see the process for how you would come up with an algorithm for writing a prime congruent to 1 mod 4 as a sum of two squares, you can see that on page 367. But then if we don't have a positive integer that satisfies the hypothesis of this theorem, then it can't be written as a sum of two squares. So 35 is 5 times 7, and 189, which is 3 cubed times 7, are not sums of two squares. Okay. But while these last two can't be written as sums of two squares, they can be written as sums of four squares. Right? Because every positive integer can be written as a sum of four squares according to that theorem of Lagrange. Okay. All right. So that's kind of the last way I wanted to apply Minkowski's theorem. Okay. So now for the brief survey bit, meaning I'm not going to prove any of these statements. I might mention how you go about proving them or where you can find the proof, but I'm not going to prove any of the statements. So this is actually done in the very last chapter of the book, which concerns the distribution of primes. So, let me see here. So, when I say distribution of primes, I mean the obvious question, which is how are the primes distributed amongst the integers, right? So if I'm looking at the integers, I know that there's infinitely many primes. That's one of the first things we proved in the course. So there's infinitely many primes. Okay. But how often do they occur? Right? And so there's various ways you can ask that question, and there's various types of estimates that you might want. Some of these statements are a lot more crude than others, which are like a lot more precise or a lot more refined. But the following theorem was once a conjecture before it was proven. It was called Bertrand's postulate. And so this was shown first, I think, by Chebyshev. So there's a theorem, which is Bertrand's postulate. Okay, it says let x at least 1 be a real number. then there is a prime number P satisfying P is strictly bigger than X and less than or equal to 2 times X. Okay. Alright. You might say, wait, why am I including this less than or equal to? I said let X be a real number, right? So X could have like 2 in the denominator or something, right? So there, you could actually have equality here. Alright. So this was called Bertrand's postulate. This is proven by Chebyshev. I can't remember when this was done. I guess this would have been the middle to late 1800s, I think. Maybe it was a little bit earlier than that. Here's the result. Simple way of saying it is that pick any number you want, right? Between that number and twice that number, there is always a prime number. Okay, so this is saying something a little more fine than there's infinitely many primes. This is giving you a better idea of how often primes occur. Okay. So, what would the proof of something like this require? So the proof that I will outline here is due to Paul Erdős, I think. So proof outlined here is due to Paul Erdős. And so first there is a key observation. Okay. So first of all, look at isolating the prime number between n and 2n. Okay. Where n's an integer. Okay. The idea is we do this by using the binomial coefficient. Using the binomial coefficient, 2n choose n has a special form. This is actually just 2n factorial over n factorial squared, or n factorial times n factorial. Okay. And this is an integer. Okay. So this fact is shown in one of the appendices in this book. Okay. So, in order to do this, the main observation is the following. So all of the prime factors of this binomial coefficient 2n choose n are less than or equal to 2n, and all primes p that are between n and 2n divide that binomial coefficient. Okay. So this is the key thing. Now, even though, even if I tell you this trick, still doing the proof is very involved. So even using, a lot of this gets wrapped up into 5 lemmas. Even using those lemmas, this is a multi-page proof. This is, let me see here. Yeah, this is an 8-page proof with the proof of those lemmas. If you don't include the proofs of the lemmas, it is a 3-page proof, roughly. This together with like 5 lemmas are used to show this fact. So I guess the question is like, what type of number theory are you getting into when you're starting to make arguments like this? The arguments that are put forth for this proof, it's very involved and it's a long proof, and it would take me more than a whole day to go through it. But actually, basically everything that we've done in this course up to now would, basically nothing that we've done, I guess, is like radically different from this proof that's presented. But it still tends towards, and most of these proofs that are done here tend toward the type of stuff that we did very briefly in 5.7, which was when we talked about the zeta function. And so a lot of these proofs tend toward analysis. They tend toward the analysis side of things. And so one of the last named theorems stated in this book, which is not proven in the book, is the prime number theorem, which I am going to state, which a proof of it is not included in the book, but these proofs are included in books on what's called analytic number theory, and I'll write that title down a little later, which is exactly what it sounds like. It is applying methods of real and complex analysis, especially complex analysis, to the study of questions from number theory. Okay, so I mean, just to give you like the absolute lowest form of introduction to it, we saw the correlation between something like the Riemann zeta function and the primes earlier in 5.7. And the Riemann zeta function being defined the way it is, of course, is something that you would see in an analysis course, defined as it is as this series. And so that gives you just a tiny little taste of what sort of methods could be used to study it. So this is the key observation of the proof. I'm not going to go through it. It relies on a bunch of lemmas. If you want to look at the proof is spread from page 494 to 501. So the proof is from page 494 to 501. If you wanted to have a look at how it's done, 5 lemmas are used. So if you take the lemmas as being true, you don't need their proof, then you can get the proof of this thing down to like 2.5, 3 pages, basically. Okay, but then I mean you're cheating, right? When you talk about the length of a proof, it's like if I have a paper that would be, if I included all the results like from scratch, 100 pages long, but I relegate everything to a bunch of lemmas, and then my main theorem is I just rattle off, like lemma 5, lemma 17, lemma 25, like just 10 sentences each referring to multiple lemmas. It's not really a short proof, right? I've tricked you. So anyway, and that's going to be particularly something that comes up when I talk about the prime number theorem here in like a minute. So we had mentioned, you're talking about the distribution of primes, ideally even, you're talking about just straight up the number of primes less than a given number, right? So recall that we used pi of x to denote the number of primes p that are less than or equal to x. Okay. So remember when I think the computation. So we have brought this up before at least to discuss very simple questions about distribution of primes. So I think in the context we mentioned it actually was talking about the number of primes that are relatively prime to a given number. Okay, or sorry, the number of integers that are relatively prime to a given number. We also discussed. But anyway, this, if we had an estimate for this, that would be nice. Well, like 200-ish years ago, so original idea, I guess, was that pi of x was like approximately x over ln of x minus some number, so 1.08366 or something. Okay. So another idea was that an approximation of this thing was given by roughly like 1.045 plus the integral from 2 to x of 1 over ln t dt. Okay, so these two were two old approximations. So the first one due to Legendre, and this one was due to Gauss. So Gauss and Dirichlet. So I think Gauss was talking about it in his notes. Dirichlet actually showed this or proposed this particular approximation. So Chebyshev in like around 1850 said that there exists constants c sub 1 and c sub 2 such that this number of primes less than or equal to x was bounded between constant times x over ln of x and other constant times x over ln x. Okay, so this, a version of this with specific choices here, is called Chebyshev's theorem, which is proved in the textbook, and it is an easier statement than the prime number theorem. The prime number theorem is very hard to prove. Okay. All right. So the actual best thing that comes out of this is called the prime number theorem. This has been referenced a bunch already in this course. I might have even mentioned it literally on the first day of class. I used it when talking about primality testing because it was kind of the thing that told us that if you had a quick primality test, well, it wasn't that bad to just start with some large odd integer that had a bunch of digits and then just check a bunch of odd integers, consecutively to see whether or not they were prime. So the prime number theorem is the thing that told you that wasn't totally a hopeless affair, because the estimate that we got for how likely it would be that a number chosen like that would be prime came from the prime number theorem. So if the prime number theorem worked differently, right, if that calculation had been different somehow, then that might not have been something that would be doable. But it turns out that prime number theorem says that the limit as x goes to infinity of pi of x over x over ln x is 1. Right. Which, of course, you could restate if you wanted to. So this is saying that pi of x and x over ln of x are approximately the same quantity when x is large. Right. So a note about the prime number theorem. So you will see this often, that this is true. Okay. And I mean, it's a pretty amazing fact. It's nice. It gives you kind of the exact type of answer you're looking for in terms of the distribution of the primes. This thing tells you, right? It gives you an approximation for how many primes you can expect up to some x. Okay. And you could actually, if you want, you could go check this, right? If it's so, the number of primes up to some not so huge number, you could actually you could enumerate all of those and just count them, so we know how many primes there are. You can check that against this approximation to see how close it is. So a couple of notes. So the first proof of the prime number theorem involved complex analysis. And when math was still kind of getting its fundamental footing, there were questions about what was allowed in a proof, or what should be allowed in a proof. So, for instance, right, there were ancient Greeks had this notion of compass and straight edge construction, which was essentially, you can almost think of it like a game. It was, what could you do with an abstractified, right, like idealized compass and straight edge, and no other measuring tools, right? No other tools. And that led to some really interesting questions. And could you double the cube? Could you trisect the angle? These sorts of questions. The obvious thing is that if you broke those rules, if you use something other than just idealized compass and straight edge, then these things that were supposedly impossible are possible, right? So like trisecting the angle, you can do that. You can even do it for some specific angles. You just can't do it generally. So with compass and straight edge alone. But the idea was you could, if you just cheat and use different rules, then obviously you could do it. So some mathematicians viewed using tools outside of the context that the theorem was stated in as almost like cheating. And the thing is that math didn't get its current foundation until the early 20th century. So it wasn't until the very end of the 1800s and early 1900s that there came this kind of like universal foundation for most of math. So these foundational questions are very important to some people, and so a lot of mathematicians definitely didn't like the fact that complex analysis was used to prove this fact when, in their eyes, it shouldn't have been needed. So since then, a number of supposedly elementary proofs have been found. So elementary here meaning that they don't involve complex analysis. But ironically, those proofs are way more convoluted and way more technical than the ones that actually involve complex analysis. This is a topic. Even some popular math and science writers remarked when Fermat's last theorem was solved in the 90s about the fact that hyperbolic geometry was used as in the proof of it as like a way of saying that it's almost like cheating. But questions like that are not we don't worry too much about foundational questions like that too much. Unless I guess you're a foundations person. There's probably some people that might still get testy over that. Another example of this is constructionists versus the non-constructivists, which so Brouwer and it was Brouwer and Kronecker, maybe. I can't remember. I think it was Brouwer and Kronecker. I can't remember if both of them were constructivists or just Brouwer was and Kronecker was not a constructivist. But so what was a constructivist? It was it's a mathematician that felt that the only proof that is valid in a sense is a constructive proof. So a proof that's not constructive, that is a proof that shows existence of something but doesn't actually construct the thing it's showing existence of, or say how it should be constructed, is like not valid in a way. So, you know, there were in the 1800s and all the way up until the early 1900s, there were, you know, groups of mathematicians that were constructivists and you know, held to this belief. And what's ironic is I think Brouwer was a constructivist, and one of the main thing I even know that's named after Brouwer is the Brouwer fixed point theorem. And the only proof I've ever seen of it is a non-constructive proof, which I thought was pretty funny. Anyway, so this is the prime number theorem. There is a weaker version, which is a form of this estimate that Chebyshev came up with. So theorem, this is call it Chebyshev's baby prime number theorem. Probably no one has ever called it that, but that's what we're going to call it. So this is let x be greater than or equal to 3. Then 1/2 times x over natural log of x is less than or equal to pi of x, which is less than or equal to 3 times x over natural log of x. So x doesn't have to be very large for this inequality to hold, and this gives you a pretty good estimate on number of primes without needing to refer to the prime number theorem. It's not as good as the prime number theorem, but the proof of this can be done without, you know, taking many chapters of side material that have nothing to do with the rest of the course. So this can actually be done with some of the stuff. It mirrors a lot of the stuff that was done in 5.7. So this is actually proved from 503 to 507 in the textbook. So page 503 to 507. Okay, is the proof of this. All right. So these are literally the last things that are in the book other than the appendices. This is from chapter 20. So we essentially touched, I believe, on every single chapter in the book. I skipped chapter 10, I think, and we didn't do anything from chapters 16, 18, or 19. But every other chapter in the book we almost exhaustively covered. 17 we only did like half of it. That was the continued fraction stuff. We did maybe about 40% of chapter 17, but so we've pretty much gone through the book. So the question is, say you want more number theory, all right? What do you do? How do you fix that problem? So where to go from here? If you really liked this stuff. My original plan was to, you know, attempt to do a couple lectures on elliptic curves, and then I decided not to. We haven't done any methods really, so the Bhaskara method is kind of like a hidden version of that, but we didn't actually refer to the picture of what was going on at all. But if you wanted to have a look at elliptic curves, So elliptic curves is one great direction that this goes. There's an undergrad text that's rational points on elliptic curves. So this is by Silverman and Tate. This is undergrad text. In math. I think that's the series of the textbook. The older version looked cool. The newer version is all shiny and doesn't have as much soul, but it probably fixes a lot of errors or something. But I really like the way the older version looks. So this is the undergrad version. Same author has a graduate version, and I can't remember off the top of my head what is the how much overlap there is, but I'm pretty sure that it is just a souped up version, which I'll get into what would kind of breach the gap between these and what you might need to have seen before you look at this book anyway. So there's a graduate version which is called Arithmetic. So Arithmetic of Elliptic Curves. I can't remember if it's of or on. This is also by Silverman. So this is a grad text. Okay. So the other thing, which I brought up throughout the course, is just algebra. If you haven't had a first solid course in algebra, then algebra is definitely the place to go, because so much of what we did could have been stated in more, we could have stated it in more convenient ways. We could have noticed more patterns. We really weren't held back at all by it. Like nothing we did in the book was held back by it, which is why I imagine the authors have written the book the way they did, so that it needs absolutely no algebra background, which is great because you don't have to have had a course in algebra to do this. For algebra, there are so many standard books here. I'm not even going to say anything here. I mean, there's Rotman, and they're all called abstract algebra. That's what they're called. So I'm just going to say a bunch of authors. So here's a book, Rotman. He might even have an undergrad text. I don't know if it's just graduate. It doesn't really matter. There's not a huge difference between graduate and undergraduate first texts in algebra. Dummett and Foote is another. Stay away from Lang because it's like a giant compilation book. I don't think anyone on the planet's ever read like the whole thing. It's more of like a reference book. Let's see, I'm looking at my shelf now. So Rotman, Dummett and Foote, that's good enough, I think. I mean, there's so many of these books. I have no idea what is currently in fashion, but basically what you're looking for in algebra is the typical algebraic structures. You're studying groups, rings, fields. That includes finite fields. You're doing modules. You're doing linear algebra in that style, not the style you might have seen in like 241 or 461. This is kind of a prereq for anything that you're going to do next. I don't even this Elliptic Curves book. I'm pretty sure I'm pretty sure that it would be definitely to your benefit to have some foundation algebra if you don't already. Stuff concerning say prime number theorem, zeta function, that kind of stuff. If you're wanting to, if that kind of part of this course interests you, we didn't spend that much time on it, of course, but this is analytic number theory. So you can look at textbook and analytic number theory. I'm not sure here what would be the best choice, but there's a lot of options. There's a book that is a graduate text that is related. So this is Modular Forms. Here's what the book looks like. I haven't looked at it in a while, but I remember this being pretty solid, because I'm not a number theorist or anything, so I'm any advice I give on textbooks is purely from, you know, like an outsider point of view. So here's the book, Modular Forms: A Classical and Computational Introduction by Kilford. Modular forms, it's hard for me to kind of try to wrap them up. They are so they're definitely on the analytic number theory side of things, but they tie in a lot of ways to some of the questions that have been related to what we've been talking about. I think that's about it. I mean, I would say that if you haven't had course in algebra yet, or if you want to take more algebra, then you're never going to go wrong with going further down the algebra rabbit hole, because that would help with anything you did further in number theory. But other than that, I would say that the next logical step is a book like this, because it's going to have a similar feel to the stuff that we did, in the sense that it's going to be there's going to be a ton of examples worked through. And what is nice about that, in fact, I was talking to someone about this, when you get to the graduate level, like a lot of the examples are pushed aside, and so you don't actually get to see a lot of stuff worked out explicitly. And so reading the undergrad text actually was kind of a lot more helpful in some ways than reading some of the graduate text. So in this case, there's a lot of examples of these things worked out. So this was actually what I was gonna my lectures on elliptic curves, I was gonna use this book. So anyway, this is just a quick list of things that you could look at from here. So anyway, I think that's about it. I think that's about all I was going to say. So that is the course. You saw the announcement yesterday when I posted your final exam. Because there's a departmental Zoom meeting that was only announced yesterday, I had to move my office hours. So instead of being from 2 to 3:30, they'll be from 3 to 4:30. So I'll post an announcement when I go live with those. So I will see you all later today, and if not, I hope you enjoyed the course. So I'll be in contact on Elms and let you all know everything. I'm putting in all the grades by your final grades will be submitted to Test Studio and all that stuff by Monday. So that'll be that. So as I said, tonight is when your final exam's due. But if you need a little bit more time, that's okay. But don't take too much time. Have it in by Sunday morning or Sunday afternoon, or it's going to be very hard for me to get the grades in on time. So anyway, that's about it. So I will see you all later.